Hey everyone, welcome. If you're a first-year programming student, I bet loops and algorithms sometimes feel, well, kind of like trying to read a foreign language in the dark. But today, we're flipping the lights on. In this explainer, we're going to completely demystify the sum of primes algorithm, and we're going to do it using one of the absolute most powerful tools in any programmer's toolkit, a visual trace table. I am super excited to guide you through this, so get comfortable, focus in, and let's decode this whole thing step by step.
So let's dive right in with a pretty fundamental question. We all know what a prime number is from math class, right? It's a number greater than 1 that's only divisible by 1 and itself. 2, 3, 5, 7, easy enough for us humans. But how does a computer actually know a number is prime? It doesn't have intuition. It literally has to follow strict logical instructions to test every single number. And setting up those instructions, that exact problem, is exactly what our code is going to solve today. Before we even look at a single line of code, let's picture the finish line. When we run our algorithm to check all the numbers up to 10, this is the exact output we're working towards. It's going to find the primes 2, 3, 5, and 7, and then it'll add them all together to give us a final sum of 17. Keep this target in the back of your mind, because every single line of code we dissect today is marching us directly toward this exact result.
To keep us on track, here's a quick roadmap for this explainer. First up, the prime sum algorithm. Second, the anatomy of nested loops. Third, reading the trace table. Fourth, primes versus composites. And finally, the square root optimization.
All right, let's kick things off with Section 1, the prime sum algorithm.
Moving right along to Section 2, anatomy of nested loops. So our overarching goal here is pretty simple. Count up from 2 to a target number, which in our case is 10. Check if each number is prime, and if it is, keep a running total. To pull that off, we use loops within loops. Honestly, the easiest way to think about these nested loops is with a boss and worker analogy. The outer loop variable I, well, that's the boss. The boss essentially says, I'm going to hand you numbers from 2 up to 10, one by one. Then we have the inner loop. That variable j is the worker. For every single number the boss hands down, the worker has to do the heavy lifting. They roll up their sleeves and divide the boss's number by different values of j just to see if there are any clean divisors. And if the worker finds a divisor, boom, the number isn't prime.
Okay, Section 3, reading the trace table. Now, trying to keep track of the boss I and the worker j entirely in your head? Yeah, that's just a recipe for a massive headache. So we use something called a trace table to track our variables like I, j, our prime Boolean flag p, and our running sum step by step so we don't get overwhelmed. Starting with I equals 2, the boss hands down the number. Our worker loop tries to start at j equals 2. But wait, the worker loop has a very specific condition. It only runs if j times j is less than or equal to I. Well, 2 times 2 is 4, which is definitely greater than 2. So the worker says, nope, condition not met. And we actually skip the inner loop entirely. Because we skip that divisor check, our Boolean flag stays true. 2 is marked prime, and our sum goes from 0 to 2. And you know what? The exact same thing happens for I equals 3. 2 times 2 is 4, which is greater than 3. We skip the inner loop, the number is prime by default, and we add 3 to our sum, bringing it up to 5.
This brilliantly shows what happens as we get into slightly higher numbers. For I equals 5, the boss hands us a 5. The worker starts at j equals 2. 2 times 2 is 4, which is less than 5, so the worker goes to work. We check if 5 modulo 2 equals 0. It doesn't. 5 divided by 2 leaves a remainder of 1, so the worker just increments j up to 3. But hold on, 3 times 3 is 9, which is greater than 5. The worker stops right there. Because we never found a clean divisor, our prime flag stays true, and our running sum grows to 10.
And we see the exact same pattern build when we check the number 7. For I equals 7, the worker checks j equals 2. 7 modulo 2 leaves a remainder of 1, no divisor there, so the worker tries j equals 3. But 3 times 3 is 9, which is greater than 7. The worker loop just stops. The number 7 successfully survives the worker loop, our flag remains true, and we add 7 to our sum, finally reaching our target sum of 17.
That brings us to Section 4, primes versus composites.
But wait, what happens when a number isn't prime? This is absolutely crucial to understand. When a composite number is found, it triggers a neat 3-step sequence. Step 1. The worker checks if I modulo j equals 0, meaning j divides perfectly into I with 0 remainder. Step 2. If that happens, we immediately flip our Boolean flag p from true to false. The number is busted, it's composite. Step 3.
At that point, mathematically speaking, there is zero reason to keep checking. The number is definitely not prime.
Let's actually slow down for a second and trace the number 9. The boss hands down 9. The worker starts at j equals 2. 2 times 2 is 4, which is less than 9, so the worker proceeds. Is 9 modulo 2 0? Nope. Remainder 1. So the worker moves to j equals 3. 3 times 3 is 9, which equals 9, so the loop runs again. Now the worker checks. Is 9 modulo 3 0? Yes. 9 is cleanly divisible by 3. Our condition is met, so our prime flag p flips to false. And because it's false, we do not add it to our running total. Our sum stays safely right where it was at 17.
All right, our final stop, Section 5, the square root optimization.
Let's shift gears from just reading code to actually thinking like a true software engineer. You might have been wondering about that kind of weird worker loop condition. J times j is less than or equal to I. Why not just check all the numbers up to I? Well, mathematically, you only ever need to check for factors up to the square root of a number. But calling a math.squareroot function in your code, that requires some pretty expensive floating point decimal math. The absolute brilliance of checking j times j less than or equal to I is that it gives you the exact same mathematical boundary as checking the square root, but it only uses fast, cheap, integer multiplication. It is a massive optimization that speeds up your code dramatically, especially as numbers get larger.
So, to summarize the core takeaways from our trace table autopsy today, we saw visually how I equals 2 and I equals 3 literally skipped the inner worker loop entirely. We learned how j times j less than or equals I perfectly avoids those expensive float square root calculations. We saw exactly how the modulo operator acts as a trap to mark composite numbers. And finally, we watched how prime numbers continuously added to our total, while composite numbers left our sum completely unchanged.
As we wrap up this explainer, I want to leave you with a quick challenge to test that new engineering mindset. Think back to our trace table. Once we found a divisor and set p to false, the code theoretically could just stop right there, right? I mean, there's no point in checking more divisors. So since p is false the second I minus j equals 0, how could you rewrite the code we looked at today to include a break statement, stopping that inner loop early and making the algorithm even faster? Think about exactly where that break statement belongs. Keep coding, keep tracing, and I'll catch you in the next explainer.